morning, distinguished members of the examination committee. My name is Ibrahim Musa, and today I will present my master's research titled Design, Optimization, and Real-Time Structural Health Monitoring using Embedded 3D Printed Piezoresistive Sensors in Composite Structures. This work was conducted at the Mechanical Engineering Institute of UNIFE under the supervision of Professor Ibrahim Gomez and Professor Marilia Sonego. The central goal of this work is to develop embedded sensing systems that can be integrated directly into structures, enabling continuous structural health monitoring through their service life. This presentation is organized into 6 main sections. I will begin with the background and motivation, research gap, followed by the objectives. Then I will discuss the literature review, followed by the sensor optimization framework, the experiment and the results. After that, I will demonstrate the system level validation using an aerospace pylon case study. And finally, I will conclude with the major contributions and the future research directions. Structural health monitoring, usually abbreviated as SHM, is increasingly getting much importance because modern engineering systems are becoming much larger, lighter, and more complex. Traditional inspection methods are typically periodic and offline. This is obvious. And as a result, damage can develop in between inspections without being detected. Now, composites and additively manufactured, structures especially require continuous monitoring because internal damage is often difficult to identify visually, and therefore there is the growing, interest in creating self-sensing structures where sensors are integrated directly into the structures rather than touching them afterwards. The aim of the work is to develop, optimize, and validate embedded 3D printed piezoresistive sensors for real-time structural health monitoring. And in order to achieve this aim, 4 objectives were defined. First, review the current state of the art. Second, optimize the geometry of the embedded piezoresistive sensors. Third, integrate the optimized sensor into a realistic engineering structure. And finally, validate their monitoring performance under loading conditions. Although embedded sensors have received significant attention, several challenges still remain. The first challenge is the issue of sensor-host interaction, because any attempt to increase the sensor sensitivity often weakens the host structure. Secondly, many studies remain limited to laboratory or coupon scale specimens, and finally there is a limited validation of embedded sensing systems in realistic load-bearing structures. This research addresses these limitations by combining optimization and system-level validation. This section presents the comprehensive review conducted as the foundation of the research. It forms one of the major 3 chapters or sections of the main thesis. And this particular section or chapter was published in November 2025 in Non-Destructive Testing and Evaluation journal. And the review followed a systematic search protocol. And we use kind of the databases we use to search for our articles for the study, the Web of Science and the Scopus. And the search terms that were used to source for these articles are 3D printing and sensors and composites. And from the Web of Science, we got 550 number of articles and 791 from Scopus. And upon application of some filters, such as elimination of some duplicates, application of some inclusion and exclusion criteria, uh, total of 93 articles were retained for detailed analysis. And these inclusion criteria are that only research articles with some experimental findings were included, and works that were published in English in the past 5 years were included, and in the field of engineering with some focus on embedded sensors for SHM, that's structural health monitoring applications. Now, for the exclusion criteria, purely theoretical studies were dropped out of the work or study, and studies published before 2020 were also dropped, and research also on sensors that are related to SHM were also dropped out of the study. From the overall findings, the overall finding of the review is presented by this kind of pie chart, and as we can see, most of the studies reviewed were conducted on piezoresistive sensors, followed by piezoelectric sensors, which form 19% of the total studies reviewed, and then fiber optic sensors, 7%, and then others sensor technologies that were used which do not fall within the categories of these first three mentioned form the remaining percentage. Now, looking closer at this kind of sub-classification one after the other, starting with the piezoelectric sensors, for each subgroup, we looked at it from three different perspectives: the process through which the sensor was implemented or developed, the material, active sensing material, and the form in which the sensor was implemented. Now, starting with the piezoelectric, we were able to see, as presented by chart A, that the predominant processes used were material extrusion and direct ink writing. Now, moving to the material, active sensing material, we were able to see, as presented by chart B, that predominantly PZT based and PVDF based materials were the predominant sensor materials or active sensing materials that were used in the development of the piezoelectric sensors. Now, coming back to the form in which these sensors were implemented, as reported by the authors of the reviewed works, predominantly, as we can see by chart C, that most of these sensors were implemented as material supportives. Now, these trends suggest that full structural integration remains challenging for piezoelectric sensors due to material compatibility requirements, and in addition to that, some specialized post-processing procedures required also before they can exhibit effective sensing behavior, such as sintering, curing, polling, among others. Now, moving to the next subclassification, which is the piezoresistive sensors, as presented by the chart A, we were able to see that the predominant kind of process used was the fused deposition modeling. This reflects their excellent compatibility with the conductive composite materials and multifunctional printing strategies. And this makes piezoresistive sensing particularly attractive for smart structural applications. Now, moving to the active sensing material, we were able, as presented by this chart B, we can see that the carbon-based material dominates the entire distribution, with carbon nanotube taking the lion's share. And moving to the form in which this was implemented, as the sensor was implemented, we can see, as presented by chart C, a kind of balanced distribution in terms of the form in which these sensors were implemented. Some were as material supportive, while some as material embedded. Now, this indicates that piezoresistive sensors are inherently more suitable for monolithic integration into structural components through additive manufacturing processes. Now, looking at the next sub grouping, that's the fiber optic sensors. Starting with the process, we can see a relative sparse distribution in terms of the process used in the implementation or integration of the sensor. And as for the material, we can see a dominance in terms of the usage of fiber Bragg rating sensors, that the FBGs, and this could be attributed to their unique and special advantages, such as the complex, high sensitivity, uh, immunity to electromagnetic interference, among others. And now, looking at the form in which these sensors were implemented as supported by the authors in the reviewed works, we were able to see also a kind of a balanced distribution in terms of material supportive and the material embedded. Now, moving to the last grouping, that's on the of the sensors, which were put under other sensors as the emerging technologies that do not fit within the classification of either piezoresistive, piezoelectric, or piezo fiber optics. And examples of which are presented in the literature are the capacitive sensors, triboelectric sensors, some self-powered sensing systems such as thermoelectric generators, among others. We were able to see that kind of a spatial distribution also in terms of the process used, but with the kind of FDM taking the lion's share. And for the active sensing material also, a similar trend was also observed. Carbon-based and ion-based sharing equal percentage, with the microelectromechanical sensors taking the remaining. And we were able to discover that most of these kind of works were also kind of implemented, or sensors were implemented as material supportives. And from the findings, we were able to discover that piezoresistive sensors dominate recent studies. Carbon-based conductive materials are most common. Fused deposition modeling is the dominant manufacturing process. Major challenges remain durability, integration, and scalability. Now, these findings directly motivated the methodology adopted in this study. Now, moving to the sensor design and optimization, that's the second major section or chapter of the thesis. This particular chapter was published January 2026 by Smart Materials and Structures. And having now established the research gap, I will now present this section. And the entire, framework follow a four-step methodology. Experiment, model, optimize, and validate. Experimental data were first generated through design of experiment. Surrogate models were developed, trained based on the experimental data generated, and multi-objective optimization was used to identify the optimal Pareto optimal designs, and then finally the best solution were validated experimentally. The geometry we adopted for our study was that of kind of conventional metal foil strain gauge. And looking at the nature of our problem, it was a kind of a multi-objective mixed integer multi-objective optimization problem. So we had a kind of many input variables, and also more than one output variable. So from our input variables, we have them also divided into two. We have some that are continuous, while some are categorical. Now, for the continuous variables, based on this particular design and adopting the two-level factorial, design, these are the trace width, the intertrace distance, the trace thickness, and the number of end loops. Now, some preliminary analysis revealed that this two-level factorial design wasn't sufficient enough to fully map the effect of these input variables on the output variables, that the sensors responses. And as a result, we resorted back to the central composite design response surface methodology, and in which we introduced some kind of a center points, and resulted into 30 total number of designs per DOE. Now, our categorical, variables or categorical input variables are the infill pattern, and the print type. Under the infill pattern, we considered the rectilinear at 45, and for the align, we consider, rectilinear and aligned. Rectilinear at 45, aligned at 90. And under the print type, some of the sensor geometries were surface printed on the host structure, while some are fully embedded inside the host structure. Now, these categorical variables are what forms the basis of our, subgrouping of our design of experiment into DOE1, where we have the sensor surface printed, taking kind of rectilinear infill pattern, DOE2 with the sensor surface printed as well, but with aligned at 90 degrees infill pattern, and the last subgrouping, DOE3, fully embedded with the sensor also taken aligned infill pattern. And we used a brand of GT Max 3D PLA, white in color, for the printing or manufacturing of the host structure, while a ground multi-conductive PLA was used for the sensor material. And of course, the process we used was a kind of fused deposition modeling, a multi-material printing process using Bamboo Lab model X1E carbon combo. And we have the typical kind of geometry of our CAD model, the CAD model of the test sample, showing how the sensor was kind of implemented on the host structure. This is just one of the designs, and we have the various designs here as suggested initially by the two-level factorial, design. So we have them as manufactured here. And for the optimization problem, we have the design vector as presented by this kind of matrix X, in which we have up to 7 different input variables. The first 4 are the continuous, while the last 3 are the categorical variables. And the objective was to maximize F1, F2, and F3, where F1 is the gauge factor, F2 the maximum working strain, and F3 the stiffness or elastic modulus of the system. And of course, this is a kind of a constrained problem, so we have it subject to the following constraints. The first one is for the categorical variables, while the remaining for our continuous variables. The entire, from optimization problem follow a two-stage methodology, beginning with the development of our meta model, the surrogate model representing the data, and then to the multi-objective optimizer, where the Pareto optimal design was selected. And we have 8 different algorithms, regression algorithms for the development of our surrogate models there, as presented by this table. And because we use a multi-objective particle C1 optimizer for the selection of the Pareto optimal design, so we have the hyperparameters as used by the algorithm as presented by this table. And we initially conducted a kind of embedding depth analysis just to see the effect of embedding on the response of the sensors. We have 3 different designs. One of the designs, we have the sensor surface integrated, and the second we have it partially embedded or subsurface integrated. And as for the last design, we have the sensor fully embedded within the host structure. Now, across these 3 different designs, we made sure we kept the geometry of the sensor constant, so as to be able to isolate the effect of depth of embedding on the response of the sensors. We have our experimental, test setup as presented by this image showing the data acquisition system, the load cell, and the test sample placing between the jaws of the load cell as well as the, data acquisition device. Of course, the load applied was quasi-static at 5 millimeter per minute. And the gauge factor was evaluated using equation 1, the linearity assessment as R squared, and maximum, working strain at the identified at the onset of the deviation of the characteristic curve, as the resistance strain curve. And the modulus of elasticity was also evaluated using equation 2 as presented on this slide. And for the embedding depth analysis, we have the piezoresistive response curves for the 3 different configurations as presented here. And every other, performance matrix was evaluated from this important, curve. And all the configurations show linear response as expected. And also fully embedded sensor exhibits as the steepest slope as presented by figure C here, which points towards higher, gauge factor values. And we have the result as extracted and is presented here. We can see a kind of upward trend in all the 3 different responses. Now, looking closer to this numerically as presented on this table, we were able to see that the gauge factor kept increasing from 4 for surface design to 7.2 for subsurface to above 15 for the fully embedded configurations. And of course, consistent value for the linearity was observed for all the 3 different geometries. And so also similar trend was observed with the, the maximum working strength. And this, behavior of the sensitivity of the geometry could be attributed to the load transfer interface. Remember load transfer interface, because for the surface transfer, so surface integrated geometry, we only had 1 load transfer interface. For the subsurface, design, we have up to 3, and for the fully embedded, as we can see, we have up to 4 different, load transfer interfaces. This is per 1 sensor trace. And we conclude by saying, okay, embedding is, even though it appeared to be a kind of simple, yet it is very powerful tool for tuning the sensitivity of the sensors. Now moving to the DOE data or experiments, we have the piezoresistive response curves here for a representative sample, the sample 3, across the 3 different, DOEs. And all the experimental data, all the data that were used for the training of the algorithm, as the regressors, and the subsequent selection of the best design by the optimizers. They used this data as extracted from this particular curves. And now we have the performance of the regressors that's during the development of the meta model, the surrogate models, and we can see that for the gauge factor, the response surface methodology performed better, while for the remaining, the GPR regressor appeared to be the best. Now, looking at taking the average performance coefficient of determination across all the responses for each and every kind of regressor, we were able to see that GPR, the model developed by GPR, appeared to show the best coefficient of determination. And therefore, for our onward, selection of the Pareto optimal design, we use the model developed by the GPR optimal algorithm, regression algorithm. And here we have the Pareto optimal Pareto fronts for the optimal solutions, and These are we have two different topses because we identified that there is a kind of a conflicting variables among the respective output responses of the sensor. So we choose to implement some technique of the order of preference in the selection of the ideal solution. For the first one, we give special attention to the gauge factor. So special yes, importance was attached to the gauge factor. So we have the result as presented by this first chart or figure or image, while the second one we gave a kind of equal treatment, equal importance attached to all the responses, and we have this as the optimal solution. Now this information is as extracted is presented here, the input and the output and the responses by this table here. And this kind of design were experimentally validated using digital image correlation, and we have kind of this as for the topsis 33%, that's equal importance attached to all the responses. We have these three different replica for the replica of the test samples for the validation, and for the topsis with special attention attached to this kind of sensitivity, we have it here, an embedded design, and because of the penalty identified with the stiffness for this particular design, that's the embedded design, we choose to scale down the geometry to see if that problem can be mitigated, and this is the result we obtain also experimentally from the scaled variant. We have the entire validation results presented and summarized by this table. For the first topsis 33, we can see that the maximum working strain and the modulus of elasticity were successfully validated with minimal error, while the gauge factor, in the case of the gauge factor, there is a very big error margin, which suggests that the model must have kind of overestimated, over predicted the results. For the topsis 70, all the responses were successfully experimentally validated with minimal error, and also this scaling, we were able to see that it successfully mitigated that effect of kind of stiffness as imposed by the embedding. And from the outcome of the optimization, we were able to see that high sensitivity design was identified to be 59. And the scaling, we were able to see that scaling also restores back the geometry, the stiffness with a value of 2.18 gigapascal, and that the sensitivity also was retained with minimal compromise. And the validation fall below 12% also for the scaled variants. Now moving to the last, main chapter of the thesis. This chapter was sent for publication to Sensors and Actuators A Physical. Currently, it is under review, and the candidate we used for the study was a kind of aircraft engine pylon. The aircraft engine pylon is a critical structural component that connects the engine to the wing or the fuselage. We have a typical example of kind of pylon assembly for a commercial aircraft. And the pylon was not limited to supporting engine pylons. It has other functions, like in the military, they use it to support the weight of the external fuel storage. It is also used to support their weapon systems. Now, why aircraft engine pylon? The answer to this is unfortunately clear: the catastrophic risk of undetected fatigue. We have a kind of a sub-figures here showing an incident that happened with UPS MD-11 flight on November 4, 2025, as captured by a security footage, showing a kind of an accident that occurred as a result of the engine separating from the wing shortly after takeoff. And this led to kind of loss of lot of lives. Almost all the flight crews were lost in the accident, and investigations revealed that the root cause to this kind of accident was an extensive fatigue cracking that occurred on the pylon structure, and that is why we feel it is a very important, candidate for our study. The framework we use followed a six-step, methodology, starting with the CAD modeling of the pylon structure, followed by the finite element analysis. From the finite element analysis, results, we identify the hotspots, and on the identified hotspot, we kind of place systematically our sensors, and the structure was then additively manufactured and finally tested and validated. The adopted, or the pylon structure adopted, was a replica of an designed by Airbus as contained in an open literature. And because the assembly is usually combine two different structures, the load-bearing structure and the non-load-bearing structure. The load-bearing supports the structural loads, while the non-load-bearing supports the aerodynamic forces. And looking at the force diagrams, as presented here, we can see the different loads this kind of design supports and how it is clamped as well. So based on this, we developed our model using SolidWorks 2024, and this model we imported it into a kind of Abacus model 2024 using explicit solver and a mesh of C3D10M size 1 millimeter, and applying a low quasi-static load of from 0 to 20 millimeter displacement at 2 millimeter per minute speed. We have these images showing the mesh as applied and how the sensor, how the structure was clamped and loaded. And for the hotspots identification, this was kind of defined as the optimal high strength uniform gradient regions, and during this kind of definition, we made sure that zones susceptible to numerical stress singularities were avoided. And based on the identified hotspot, we kind of implement kind of a redundant sensor architecture so as to address one of the prevailing problem, which usually arise as a result of having the sensor embedded and failing during the service of the kind of the structure, and the infrastructure manager usually is left with two dilemma, having to choose either between changing the entire structure, which is going to be a very expensive option, or to abandon the monitoring program, which is going to be risky as far as the infrastructure is concerned also. So we choose to implement this redundant sensor architecture also. So we place them as pairs, first pair and second pair. So each pair is supposed to measure the same information. We use fused deposition modeling for the development of the structure, and we use this protoposter for the sensor, and standard Ultimaker PLA for the host structure. We use also Ultimaker S7 3D printer to develop our model. And we have the experimental test setup as presented by this image, and a typical dashboard of the data acquisition is also presented by this image. We have, as presented by this image, a comparison between the numerical and the experimental results. We were able to see a kind of a strong agreement between in the hotspots location between the experimental and the numerical results. Now we have the strength evolutions also from beginning to the end, and these were kind of subgrouped into three. The evolution one, which present the elastic initiation phase from the stage 1 to stage 4, and we have the second evolution presenting the hotspot development and the asymmetry manifestation as a result of the load fixtures. And we have the final stage, which is the progressive localization and premature saturation. And for the piezoresistive response of the 4 different pairs of the sensors, we were able to see that the first pair display relatively consistent results as presented here by the gauge factor and linearity, while for the second pair we can see a kind of clear margin in terms of the gauge factors. Now this was as a result of the misalignment or asymmetry introduced by the load fixtures during experimental testing. And we have the real-time monitoring as presented here, and the same issue was observed zooming at the magnitude of the amplitude for sensor 3 and 4. And from this real-time monitoring, we're able to see a high temporal synchronization with the strain evolution, and negligible viscoelastic lag was also observed during the strain holds, and it was successfully able to capture transient structural events, and that's during the load ramps. And finally, and very importantly, it was able to detect that asymmetry that was introduced by the loading conditions. And in conclusion, we were able to kind of prove that the experimental model optimized and validated framework was successfully implemented, and that the optimized geometry was gave a gauge factor of 59, and the scaling of the restored back the hotspot, the hot stiffness without sensitivity compromise. And the finite element guided sensor placement also confirms successful system level deployment. Embedded sensor network, also enabled real-time monitoring. And finally, future work should explore alternative material systems beyond just PLA, CPLA. I would like to sincerely thank my supervisors, colleagues, UNIFE, the Institute of Mechanical Engineering, the founding agencies, and members of the examination committee for their guidance and support. Thank you very much.